Welcome to this tutorial on a well service for ongoing maintenance, or AWSOM. This tutorial discusses the why of AWSOM, not the what, who, where, when, just the why. Why we've done things. Why are these solar cells orthogonal? Why? Yeah, you get the idea. The whole purpose is to make sure that anyone following us or developing it further will know the reasons for the particular decisions that we've made over the past 4 years. We spent 2 years developing it and another 2 years testing, roughly. This is the version 2019, was in testing in Tanzania for about a year, and this is the version 2020, which went sent out last month. We're talking about the why and the lessons identified along that, and the reasons there. Well, in quick summary, the housing must be IP65 or better. We must use an internal heat shield to postpone the temperature peak. We must keep the solar cells apart to allow for thermal expansion. We've got to use voltage regulators for the texting module with 3 volts input. 3.8 is not good enough because they self-oscillate. We'll come on to that in a minute. Must use silicone grease on rubber seals, not Vaseline. We use a shallow tray with ellipse on to hold the spout. It's got to be mechanically robust, orthogonal solar cells. We've got to make sure the well ID is incorporated into each computer, and the solar cell adhesive have got to be 2-part epoxy. There's a whole load of other things, but that's basically the top 10 items. There is an ancestry to these prototypes. We started off with this one. It's like a rat's nest. We're using a talking calculator, which worked very well. That was within 3 weeks. Produced it, worked fantastically, but it was taking 10 watts, far too much current. Then we went through to talking calculator again, which took very, very small current, but it was the relays and the couple of Arduinos, mini computers, that also took too much power, 5 watts. And then we moved on to this one in 2018, which was all one Arduino, one little mini computer there. I'd never programmed Arduinos before, and so it was a big jump to go from here through to here, but it was absolutely fantastic. These Arduinos are fantastic little devices, wonderful computers. But anyway, more of that than on. This has been a little mini production line, trying various things out. And what is the purpose of this unit? Well, the purpose is to produce a chart like this. And this was the actual chart received from one of the wells during latter part of August. This was received from Tanzania, and it was wonderful. How does it get onto that screen? Well, it comes through a text message. This is the texts from the various wells, and the details of the text are here. The pump count is the key, 148 showed there, and that is the amount of water flowing from that well in that particular time period. There's other information there, but engineering stuff. Right, let's have a quick view. I don't know whether you can see this, probably not, but not to worry, of the well maintenance system unit's activities. We've got 3 views. We've got everyday user, engineering user view, and the units view, the AWSOM units view. The everyday user view is, it sends a text, normally cumulative, of activity count in 30-second blocks every night. Engineering view, well, it sends text, but also the minimum temperature since the last text, the current battery voltage, the battery voltage at that time, shall we say, the activity count at that time, of course, the day count, the number of days it's been operating, and the powered up time. It's the number of the powered up time in 30-second units since the last text. Circuit diagram, here we go. There it is. Now, the idea is to say, go through this and explain what each system does, why it's there. Now, there are a couple of things that we could remove, and I'll mention that as well. But if you really want to know some of the detail, that's what we're going to discuss now. Now, this can be summarized in 6 blocks. There they are. We'll go through each of the blocks. We've got, starting on the left hand side, we've got the solar cells. Then we've got the motion module, item 2. Then we've got the computer, the Arduino Mini Pro, 3. Then we've got the nickel metal hydride batteries and charger, power switch, 4. Texting power supply, 5. And the texting module, 6. What does the unit look like inside? Well, there it is. That's the one that's been in Tanzania. That was sent to Tanzania and has come back after a year. And there we have it. That's the real deal now. Those blocks, I have put a little yellow sticky on them all. You can pause it and have a look at them. But right, now let us look at the blocks in turn. So we're looking at the solar cells now. Just that plug there. We must use proper plugs. We used little tiny ones before, but they're really not robust enough. The plugs on the circuit diagram with the radio spares, RS components, we think are really excellent. The solar cells are orthogonal. Why? Because if the shadow drops across here, this won't work, but this will still continue to work. One of the cells will work. That's why they are at right angles to one another. Internally, we have to have a heat shield, and that's what this foam lining is. It doesn't keep it warm, it tries to keep it cold. The night time is cooler than the day, so the idea is that this will introduce a thermal lag. Now, I've cut one of the cases in half, and you can see that the IP65 is really quite well sitting down there. Mustn't get any dirt in there. Absolutely key. Must not leak, because if it leaks, you get corrosion of the circuit boards. But we're talking about the case in the solar cells. If the solar cells are packed too closely together, then the coefficient of expansion of the solar cells and the IP65 housing is slightly different, and so they buckle up against each other. It bends, as you can see, and it breaks the epoxy and they come off, which is not a good thing to do, and that's what's happened here. It arches and it's bent. The last thing I want to talk about in the solar cells and housing is the base plate. Now, it looks just a bent bit of aluminium, but almost embarrassed to mention that it's taken me 3 weeks to think about this. The idea was how to fix this unit, the AWSOM unit, onto the spout, because just using these, I used a flanged box tie wraps. It could just rotate, and just to put a little back to it, which made it much more secure, which was great. Now, one thing I would suggest, one of the lessons learned maybe, is that in future we would really like to put a side on here. So we put a little 1 centimeter side on it, so it sits in a tray, so it makes it more difficult to remove. Obviously we'll have to put water holes in the tray to make sure the water drains away, but that's one of the lessons learned. Right, summary then of the lessons identified, not necessarily lessons learned, but identified of the solar cells and housing. Firstly, the housing must be robust, must be IP65 or better. We must keep the solar cells apart to allow for thermal expansion. We must use an internal heat shield to postpone temperature peak and reduce the peak duration. Consider orthogonal solar cell orientation. If necessary, use silicone grease on rubber seals, not Vaseline. We could use a shallow tray to hold the unit on the spout, and the solar cells are remarkably robust. And that concludes that section. Right, now we're on to section 2, motion module, or the radar. Radar place is that little unit there. It's a 3-pin device. It is actually a Doppler radar, 3.2 gigs. It's not 2.4, but anyway, it's a few gigs, and it actually is Doppler radar. So it sends out a pulse. Anything moving in front of it, it will reflect that 3 gigahertz pulse, and with a frequency shift, Doppler frequency shift, that little unit then detects that frequency shift, converts it into cleans it up into a nice 2-second digital pulse. It is fantastic, and it's all done with that little tiny unit there, and it's all for a couple of quid. Phenomenal, absolutely phenomenal, wonderful device. What are we lessons learned on that? Well, then we've mounted it at 45 degrees because the idea was to radar to point down to the spout. The water, there we are, it's a 45-degree thing, to down through the unit to the spout and up to the person pumping the spout, pumping the well. But there's no need. It seems to be fairly omnidirectional, that radar. It's not, but it's not bad at all. So we could use it flat. It needn't be at 45 degrees. Key point here, after turning the radar on, it needs a few seconds to stabilize, several seconds to stabilize actually. The radar's output is excellent. It's 2-second digital pulse. Power supply voltage is wide and tolerant to change, and the Doppler radar detects movement in the case that it is 6 to 10 feet. Outside the case, it can go to 20 feet or more. Right. That's item 2. What's next? The computer. Arduino Mini Pro. Where is the computer?